I know. we're gonna look over it. The good thing is we weren't really too far into the section, so it's not like we've lost a bunch of it, but we'll recap. Okay, so we are going to be on page 84, but up to this point, if you just look at the top of page 84, we kind of had two graphs we were analyzing. We had the exponential curve and then the kind of rational curve, 1 over x, and then e to the negative x. And we saw how they both had a similar shape in terms of their graph, but when we were analyzing the area under the curve, somehow this area was finite, like it equaled a number, whereas if we looked at this area, that equaled infinity. Okay, it wasn't finite, it kept going on and on and on. Remember those? Okay, so what we're going to investigate in this section is when do we know we get a number and when do we know that we get infinity. Okay, we're going to take a look at two terms today. If your area value is finite, you get some type of number. That's what's called convergent. And if your area value is not finite, okay, it kind of goes on and on forever towards infinity, that's what's called divergent. Maybe you've heard those terms before. I was always kind of an earth science geek when I was in high school, and I was fascinated with like natural disasters and death and destruction and all that. So when we were going over plate tectonics and volcanoes, you may have heard those before, like with the different types of plate tectonics, how they diverge or converge, create volcanoes, if you're familiar with those. Okay, so what we're going to do is just take a look at a bunch of examples in this section. It's titled improper integrals, so we know we should be having some type of an infinity value somewhere, perhaps in one of the integrals, because we're going to go on forever towards the right. Okay, we're going to figure out what the area looks like underneath the curve. So we're going to take a look at some patterns today. Cameron, if you get too cold, you can shut that. Okay? All right, so if you take a look at the first one, we have the integral from 1 to infinity of 1 over x to the 3/2. So notice how that's kind of similar to the one that we did before. Okay, just as a refresher, we said 1 over infinity of 1 over x. Oh, you can't see that. That was divergent. So these look fairly similar to the one that we already know diverges, but let's go ahead and see what these results might be. So if we were to do these by hand, how might you want to solve that integral? 1 over x to the 3/2. No calculator? Let's see, instead of having the x in the denominator, can we move it up top? Yeah, that would make it a negative power, right? Can we work backwards from there? Kind of reverse power rule. If you add 1 to the power, you get negative 1/2. Divide the coefficient by that new power. 1 divided by negative 1/2. Negative 2. Let's see, instead of having a negative power, maybe you want to make it positive again. You can move it back down to the denominator. Alright, now this is where it gets tricky because one of the bounds is infinity. Remember those growth rates we talked about at the very beginning? We filled out that big chart in terms of our different functions, which one grew faster than other ones. That's what we're going to kind of have to think of here when we are plugging in infinity, because technically we're plugging in a very, very, very large x value. So we got to think about, since this is a fraction, what is growing faster for those large x values. So if you think about what type of function negative 2 is versus what type of function x to the 1/2 is, which one's growing faster? If you have to reference that chart to help you out, you can. What do you think, Eric? X to the 1/2. You have a constant being divided by a power function, x to a power. So if you have the faster growing function in the denominator, what is your result from the division? If you have something small divided by something large, something that's growing faster, yeah, you're getting closer to 0. So when you plug in that top bound of infinity and you analyze that growth rate, your value would be 0. So that's what we get when we plug in the top bound. Now we have to subtract what we get when we plug in the bottom bound. So if we plug in 1, we'll get negative 2. So in the end, we have 2. So it's a little interesting. Notice how the integral of 1 over x diverges. Okay, we have an infinite area, but the integral of 1 over x to the 3/2, okay, which is, this is technically 1 over x to the first versus 1 over x to the 1.5. Okay, so just a slightly larger power, and somehow we are converging. We actually have a finite area. So there has to be some kind of cutoff point here where you go from being divergent to convergent. We're going to investigate that. Let's go ahead and try the other ones. We could rewrite 1 over x squared as x to the negative second. Let's see, if we do our reverse power rule, we'd have negative 1 over x to the negative first. Alright, if you plug in your top bound of infinity, you gotta think about your growth rates. Which one's growing faster, and therefore what are you approaching, or what's your value? 0, okay. So we have 0 minus negative 1, which would just be 1. Okay.
Testing, I'm just pressing the speaker. Thank you, have a great day.
Thank you. Alright, let's try the last one.
Testing, 1, 2, testing. Just pressing the speaker. Have a great day.
That's funny. Can we get 1/2? Sound about right? Okay. This is going to be a very not loaded question, but I'd be surprised as long as you didn't look forward in the notes. Can you find a connection between the power that you start with and the convergent area value that you have? It's a little tricky. It's okay if you can't. We can't see it right off the bat, right? No. I mean, some of you are thinking, okay, well, 1 is 1 less than 2, but notice how this isn't 2 because that's 1 less than 3. And okay, so there's something a little bit more going on with this. What we're going to discuss here is what it actually converges to and how we can determine, first of all, if it converges or diverges. Like, do we get infinity as an answer, or should we get a number value as our area? So, little fun fact here. For any a value bigger than 0, okay, where a is representing your lower bound, this format of 1 over x to a power converges, okay, meaning you get a number, if the power is bigger than 1. So notice how the 3 examples we just did was a power of 1.5, a power of 3, a power of 2. All of those are bigger powers than 1, and we got a number for all those values. However, this integral diverges, meaning you're going to get some type of an infinity value, could be plus or minus, okay, we don't know, if the power is less than or equal to 1. So that's why when we investigated the last function of 1 over x, the power is 1, okay, it diverges. And anything less than 1 will also diverge. So this kind of value of 1 is the barrier between if it converges or diverges. Okay, so you're going to always try to compare to 1. These are called p-series. Probably no surprise there because we're talking about powers. That's why we use the letter p. So we're always looking for 1 over x to a power. Now, if the power is bigger than 1, and we know it converges, we actually have a way to determine what it converges to. Okay, what is that special area number? Now, what's a little bit more specific with this one is that your lower bound must be 1. You see that right here? You see how that's 1 versus the last one was a, it could be anything. If the lower bound is 1 and you have a p-series with a power greater than 1, you can automatically conclude that this is what it's going to converge to. 1 over p minus 1. So if you look at the 3 other examples that we did, okay, for instance, part A, the p value was 3/2, 1.5. So if we did 1 over 3.5 minus 1, that'd be 1 over 1.5, which is 2. And wasn't that the area value we had? Okay, so this convergence value, 1 over p minus 1, is very specific. You have to have a p-series with a power greater than 1, but your lower bound must be 1. If it's 2, doesn't work that way. Okay, so it has to be 1. If it's 2, it still converges, right? Because 2 is bigger than 0. It just doesn't converge to this. Okay, so the lower bound has to be 1. We're going to take a look at this a little bit further. And for you kind of humor people, you can go ahead and read that statement there. I thought that was kind of funny.
We all got it.
We all got it?
We all got it.
Yeah. All right, it's all about the number 1, I guess. Okay, so you have to compare if the power is greater than 1 or bigger, less than 1. Wow.
One last time, we're testing the speakers. Testing 1, 2, testing 1, 2.
Third time's a charm. All right, so maybe we can do some of these fairly quickly just by noticing certain things. Okay, so if you take a look at the next one, instead of having to actually go through the integration, which you technically could because we're getting good at integrating, if you can notice the kind of shortcuts or particular characteristics, maybe we can determine if it converges or diverges and what that special area number might be. So taking a look at this one, let's first determine if it converges or diverges. What should we be looking for? P-value. P-value. All right, so what is the p-value? 2/3. Is 2/3 bigger than 1 or smaller than 1? Smaller than 1. Okay, p equals 2/3, which is smaller than 1. So, what's that telling you? It converges. Does it? Does it converge? It diverges. Okay? So we'll say the integral from 1 to infinity of 1 over x to the 2/3 diverges. All right, we don't know if it diverges to positive infinity, negative infinity. Mostly it's positive infinity, most cases. Okay, but we don't really care because we know it's going to be some type of an infinity value. What about the next one? P-value? Larger than 1.1, which is larger than 1. So what does the integral do? Converges. Okay, so we know it converges. Now we have to pay close attention. If the lower bound is 1, we could figure out what it converges to. Is the lower bound 1? Yes. Okay, if this was a 4, could you figure out what it converges to? No. Okay, the lower bound has to be 1. So it converges to, and we're specifically going to figure it out. So instead of going through the integration process, we're going to use this little pattern or connection to help us figure out the area value. We need 1 over the power minus 1. So we have 1 over 0.1, which is 10. All right, C is a little different because it doesn't really have that format of a p-series that we're looking for. We want 1 over x to a power. Can we rewrite that as a p-series? What would that look like? 1 over x to the 7th, okay? So our power is 7. Notice how at the initial glance at it, you might think it's negative 7, okay, but that's not the case. We want it to be 1 over x to a power. 7 is bigger than 1. So what does the integral do? Converges. So the integral converges. Is the lower bound 1? Yes. So we should be able to figure out what it converges to. We need 1 over the power minus 1, which would be 1/6. We doing okay? All right, let's go ahead and try to rewrite the next one. Okay, can we make it look like 1 over x to a power? Think about some properties of integrals that we could try. We need this to be 1 over x to the something. We can take out the 3, yep, kind of factor it out, pull it out. 1 over x to 3 halves, good. Okay, so the power is 3 halves, which is bigger than 1. So the integral converges. Is the lower bound of the integral 1? Yes, so we can figure out what it converges to. All right, so we need 1 over the power minus 1. What do you think this coefficient of 3 is going to do? Because that's a little different than the other ones we had. How do you think that coefficient of 3 affects the convergent value, your area value. It's a multiplier, yep. So we're going to have 3 times 1 over 1/2, which would be 2. So it looks like we converge to 6. We doing okay? Those are p-series, okay? It's all about the number 1. You want to first compare the power. Is it bigger than 1 or smaller than 1? And then if the lower bound is 1, you can figure out what it converges to. 1 over p minus 1. Okay, so many 1s there. Let's try the next one. This one's not exactly a p-series, right? It kind of looks like it. We have 1 over something with x to a power, because you can rewrite that as a 1/2 if you wanted to. But since this isn't a p-series exactly, we should probably go through the actual integration to help us figure out if it converges or diverges. So if you have 1 over that square root quantity, how might you want to go through the integration if you think about your techniques? Reverse power, we have u sub by parts, partial fractions. I'm leaning that way too. What do you want to let u be? 3 minus x, okay. So derivative would be -1. If we rewrite the integral, we have 1 over u to the 1/2. And then dx would be -1 du. All right. Can we work backwards from that? Maybe you want to bring up the power, make it a -1/2. Let's see, add 1 to the power, divide the coefficient by the new power, and we'll substitute in the u. All right, if we plug in the top bound, we'll have -2 square root of 3. And if we plug in the bottom bound, let's see, we're subtracting a -2 times the square root of 3 minus a negative infinity. So it'd be 3 plus infinity, which is basically an infinity. And if you're subtracting a negative, that's the same as adding. We're not necessarily doing growth rates in this one because we don't have a fraction. We can't really compare what's growing faster in terms of the numerator or denominator. So for this case, since it's not a fraction, we're just going to physically think about plugging in infinity and see how that affects our value. So if you have -2 square root of 3 plus 2 times the square root of infinity, what do you think your value is? You take a really large number and square root it, multiply it by 2, and then you're going to subtract 2 square roots of 3. Can you think about a specific number value or what's going on there? It's going to be infinity, yep, really large number. So it looks like this integral diverges. Okay, it has an infinite area. We doing okay? So it looked like a p-series, but not quite. So we actually have to go through the integration process. All right, so for these improper integrals, yes, we're looking for infinity values, but we're also looking for perhaps there's a discontinuity somewhere within the bounds. So we could have an infinite interval of integration, which is kind of like that example where you go from negative infinity to positive infinity. You could have a discontinuity on the interior of the integral. For instance, you have a vertical asymptote somewhere happening in between the bounds, so we're going to check that out. Or maybe you have a combo of the two. So for these improper integrals, you're either looking for an infinity bound or some type of discontinuity between the bounds. The rest is probably good. We already discussed the difference between convergence and divergence. All right, let's just try the next example. Let this function be e to the negative 2x. We're going to let R be the unbounded region in the first quadrant. We're going to find the volume of the solid as we revolve it around the x-axis. Let's go ahead and get a little picture first. So when we graphed e to the negative x, whenever we started this section, it was this exponential curve. So e to the negative 2x is going to be very similar, it just might be stretched a little differently. And it looks like we're wanting the area from 0 to infinity. So in terms of the shading, we can do this. And if we were to revolve that area around the x-axis, can you guys visually see kind of the shape that you would be creating? If we revolved it, we would have kind of this mirrored area underneath the x-axis happening as well. Can you visualize that if you were rotating it? Okay. So it's kind of going to look like a horn almost. So we're trying to figure out the volume of the horn. All right, let's go ahead and set up our volume integral. Can we figure out the bounds? Can we figure out the equation? It's been a while. 0 to infinity, okay. You got coefficient of pi, yep. Okay. If you're trying to figure out volume, okay, where's that word in here? If you're trying to figure out volume, you need to integrate the area. Okay. Now we talked about area of cross sections. Remember when we did the Play-Doh activity? We had like rectangles and triangles and semicircles, all those. But if you're rotating something, the area